Hello everyone. Through this video, let me explain the analysis of a series RLC circuit. So consider a series RLC circuit where a resistor, inductor and capacitor are all connected in series and is excited by an voltage source. Let the source of excitation be an AC sinusoidal voltage source, which is represented as Vm sin omega t. And now applying KVL for this circuit, we could write V is equal to VR, the voltage drop across resistor, plus voltage drop across inductor, plus voltage drop across capacitor. And we are familiar with analyzing the resistive, inductive and capacitive circuits separately, and hence VR is written as I into R and VL is J omega L into I, and VC is minus J I by omega C, where omega L is written as XL and 1 by omega C is written as XC. In this expression, I is common in all terms, and hence we take I commonly out of all terms. And hence V is written as I into, and on cross multiplying we'll have V by I, that is the ratio of voltage phasor or phasor voltage to phasor current, which is impedance, and impedance is equal to R plus, here again J is in common, so R plus J XL minus XC. And looking at this complex number, we could say that we have two possibilities. One is where XL is greater than XC, and the other possibility is where XC is greater than XL. When XL is greater than XC, we call it to be predominantly inductive. And if it is the other way, if XC is greater than XL, we call it to be predominantly capacitive. Now let me first explain the predominantly inductive case. And let us start by drawing the impedance triangle. And we have resistance. And when our circuit is predominantly inductive, XL minus XC is going to be positive. That is, this is XL minus XC. And the sum is going to give us the magnitude of impedance, and this is the angle phi. So phi is equal to tan inverse of XL minus XC divided by R. And we know the value of phi could range from 0 to plus 90 degree. So phi ranges from 0 to 90 degree. And this is a case. And here for this predominantly inductive case, let us trace the Phasor diagram also. So in all elements, current is in common. So along the reference, we take current. And when current is multiplied by a factor R, we have VR. VR is represented in red color. And we said our network is predominantly inductive, which means the inductive voltage drop will be greater than the capacitive voltage drop. So this is the inductive voltage drop, and capacitive voltage drop, which is along the negative imaginary axis, is little lower than the inductive. So let me measure the length of VL and this is VC. And now let us take the difference of voltage. So let the difference in voltage be represented using rose color, which is VL minus VC. So we have three voltages, and the sum of these three voltages, so the sum of these three voltages gives us the phasor voltage or the applied voltage V, and the angle between I and V is said to be the phase angle. So this is the phasor diagram, and when we draw the related power triangle, so this is going to be the value of active power, and the reactive power is consumed by the network because it is predominantly inductive, and S gives us the value of apparent power. And we know S is equal to P plus JQ, and the expressions along with units are the same for as we have discussed for the other circuits. Now let's discuss the predominantly capacitive case. So when our circuit is predominantly capacitive, XC is greater than XL. And now drawing the impedance triangle, will have resistance XL, and this is XC. So XL minus XC, XL minus XC will be negative because XC is greater. And hence we have the net reactance along the negative direction. R plus JX is Z. So we could also draw something similar to a phasor diagram, and let us say that here we have a triangle and this is the impedance triangle. And now, as we have seen here, after drawing the impedance triangle, let us draw the phasor diagram also. So we have current as our reference. Current acts as the reference. And current, when multiplied with the factor R, we have the voltage drop VR. And we know we have two more other voltages, which are VL, the inductive voltage drop, which is small when compared to the voltage drop across the capacitor. So adding these values, so now VL minus VC will be negative, and taking a phasor sum of all these three voltages, we have the phasor voltage, and this makes an angle phi with current, where phi is between minus 90 degree and 0. In both the cases, cos phi, the power factor is going to range from 0 to 1. And if you draw the related power triangle, it's going to be, here we have the reactive power and real power, and reactive power is supplied by the circuit. So it is drawn in the negative imaginary axis direction, and we have the apparent power, yes, and this makes an angle phi, and we know S is equal to P plus, sorry, here it is P minus JQ. And looking at this, we could say that minus Q, and hence being a capacitive circuit, our circuit supplies reactive power. Thank you.